So let's welcome Anamay. He is going to talk on is there an algebraic natural proofs barrier? So
Uh,
Anamay, stage yours.
yeah, okay. Thank you, Poonam, for the introduction. And I think I should also thank Arkadev for setting up algebraic complexity very nicely. So I'm going to talk about a possibility of an algebraic natural proofs barrier. I mean, it's fine if you don't understand what one of those things means. We'll go through those things. So this is a combination of two joint works, and yeah, so these joint works are with Preruna, Mrinal, Ramya, and Ramprasad. Mrinal is at IIT Bombay. All the others, all of the others are at TIFR Mumbai. Okay, so let's start. Oh, and I also promised that this is the last algebraic complexity talk in the symposium, so you don't have to bear us anymore. Okay, yeah. So for one last time, let's look at computing multivariate polynomials. Okay, and this model has been talked about a lot in the last few hours. Okay, so what you have is you want to compute some polynomial, and this polynomial is over some field f and some variables x1 through xn. And a very natural way to do this is to just repeatedly and like appropriately add and multiply like things that you have. Start with variables and constants, and then you'll have more and more complicated polynomials. And everything and anything that you can compute using finitely many such steps will be a polynomial. Then we'll use f to denote polynomials generally. Okay, and so if you just draw out this process, if you just try to draw this process on a piece of paper, then you'll get a directed acyclic graph, which we call a circuit. Okay, and yeah, so yeah, and because we are doing algebraic computation, we'll call this an algebraic circuit for the polynomial f over the variable x. So one parameter of interest that we will need in this talk is the number of gates used by this circuit. So gates are basically these addition and multiplication operations. This is essentially the number of operations used in this circuit C. Okay, and then we can analogously define size of a polynomial. So size of a circuit is the number of operations the circuit uses, and the size of the polynomial is the minimum number of operations required to compute f on any given input, right? Which is captured exactly by the size of the smallest circuit used to compute f, right? So this is a very nice complexity measure for a polynomial. Okay, and so for the rest of the talk, we'll use little n or capital N for variables and little d or capital D for degree. And unless mentioned otherwise, the degree will always be polynomially related to the number of variables n. Okay, so these are called low degree polynomials. So we'll only be dealing with low degree polynomials throughout the talk, unless I explicitly mention otherwise. Okay, so now we have a nice measure for polynomials. So what can we do using these? We can classify things as easy and hard. So let's first look at easy polynomials. So also, like most of the things on this slide will come from, will trace itself back to the seminal work of Valiant in 1979 or 78. Yeah. Yeah, so first we look at easy polynomials or just efficiently computable polynomials, which is also called Valiant's P or just algebraic P, right? So what are these polynomials? Is very intuitive now since the degree is polynomial related. This just means that you are looking at the polynomial families, just collection of polynomials of larger and larger number of variables, such that the nth polynomial, which depends on n variables, the size of the nth polynomial is just poly in n, right? It's efficient, so it's efficiently computable. And a very sort of a canonical example of this class, this VP class, is the determinant polynomial, which also has been introduced several times in the last few hours, in the last few talks. So what is this again? So this is just you take the basically you take the determinant of an n squared variate matrix. And how is this matrix defined? So the ijth entry is an n cross n matrix, and the ijth entry is a fresh variable xij, right? And here this sgn just means the sign of the permutation. It is either +1 or -1, right? And this is the determinant polynomial. So once we define everything this way, what is immediately clear is that, or rather not very hard to show, is that a random polynomial is hard. What does it mean? If you just take a random polynomial of on n variables of degree, let's say n, okay, And what do you mean by random polynomial? You just sample every coefficient at random, uniformly at random. So then you should expect that the cancellations, or I mean the trickery that Arkade was talking about in the previous talk, the thing that you can do by stacking up layers of additions and multiplications one on top of the other, there should not be much scope of doing that, because these things are not correlated at all. The coefficients are not correlated in any sense. Okay, so that tells you that a random polynomial should be hard, and it turns out to be hard using some dimension counting argument. And here by hard, we just mean it is outside VP. It's not efficiently computable. But but a problem with this is that this is not an explicit hard polynomial, right? I mean, so you would want, I mean, if someone asks you what's a hard polynomial for algebraic circuits, you should be able to tell it to them. It should not be like, oh no, just take a random polynomial. But yeah. So then the question is, I mean, what about explicit hard polynomials? So yeah, so in one way to define explicit is to come up with what is called efficiently definable or efficiently describable polynomials. This was again defined by Valiant in 1979, and this class is now called Valiant's NP or VNP, and we'll see what this is. So I won't define it. The definition is slightly technical. So here what we mean is that in the nth polynomial, so earlier we were saying that you should be able to compute the whole polynomial efficiently. Now we will just say that in the nth polynomial, if I point to a certain monomial, right? So suppose you have a polynomial, and I ask you, okay, so here is a monomial. What is the coefficient? You should be able to compute that coefficient efficiently in time poly n. Okay. So this is just one sufficient criterion to be in VNP. There are of course more polynomials, but this is definitely, I mean, all such polynomials and such polynomial families are definitely there in VNP, and this is intuitively this is explicit, right? Yeah. And a canonical example of this class again is the permanent polynomial, which is a close cousin of the determinant polynomial, which you can see, which Arkadev also mentioned, right? So just this sign disappears. You just sum up all the permutation monomials, right? And as Arkadev had pointed out, this is complete for a well-defined notion of completeness. This is complete for the class VNP. So this is truly the canonical explicit polynomial, if you buy my definition of explicitness to be just VNP. Right? Yeah. So now the question of finding explicit hard polynomials is just the following. You are just asking if VP is equal to VNP. Is every explicit polynomial also efficiently computable? Right. So that is the question, and this is wide open, right? But let's just see what all is known. I mean, so these are some of the known hardness results. So remember, what do we want to do? We want to find explicit polynomials that are not computable by poly-sized algebraic circuits, unrestricted completely. Commutative, non-monotone circuits. Okay. Yeah. So where have we reached? So there are a lot of structured models like non-commutative models, which Prerna spoke about, monotone models that Arkadev spoke about, then multilinear formulas, homogeneous constant depth formulas, and so on. So formulas, as these people had mentioned, it is, so these are circuits where the underlying DAG is just a tree, right? You are not doing any reusing. You are not reusing any computation. So there are a lot of results. Okay, there are super polynomial hardness results against many variants of structured models. Okay, but on the flip side, when you go to general models, so suppose you go to circuits, then the best hardness result that we know of is n log d, which is not even super linear if you insist on being pedantic. Okay, and the best hardness result for formulas is again quadratic. It's just n squared, and both of these results are tight. Okay, so a natural question looking at all these things is, I mean, why are these? I mean, we have such good results for structured models. Why are they not extending to the general case, right? And one reason could be that so all these results, right, especially the ones that I've mentioned in blue, right? All these results they can be proved using natural techniques, what are called natural techniques, and we'll see what I mean by natural techniques here, right? So then the question is, I mean, okay, so what were we trying to see, right? What is the problem? Why are we not getting strong results against strong models? And so a natural question looking at all these results is that, are these natural techniques sort of insufficient to prove strong lower bounds? Okay, so now we'll see what we mean by natural techniques. So what are natural techniques? So let's just be slightly more general for now. Let's not focus on polynomials. So suppose you have a certain universe, okay, which has a lot of objects that you want to study. So maybe you can think of polynomials. Okay, so there is a universe which has all the polynomials that you care about. Okay, and in that whole universe, there is a certain set of simple objects or simple polynomials. Let's call it C. Okay, and there is also another set of explicit objects, right? Let's call it D. You can think of C and D as computable and definable if you want. Okay, so one of the things, I mean, so what do we want to do? We want to find an explicit thing that is not simple. Okay, suppose that is the goal. And this thing is particularly tricky when it is hard to prove non-membership in this class of simples. Right? If you can just prove non-membership, then of course you'll find something explicit that is not a member. Okay, so especially when non-membership is difficult, like in the case of VP, right? So then what is natural to do is to come up with another set, let's call it P, which is the set of all weak objects. Okay, and you would want, I mean, a good weakness set P will contain everything that is simple. Everything simple should be weak. Okay, and one particular property of this set should be that proving non-membership in this set should be easy. Okay, and once you are in this setting, you will expect that, I mean, because of the easiness. So if suppose this weakness is also somehow easy to capture, which is what we mean by non-membership being easy, then you would expect that there is something explicit which should also be non-weak and provably non-weak. Okay, I mean, not like permanent and VP. I mean, we sort of believe that permanent is really hard, but we can't prove it. So, but if you come up with an easy weakness that and suppose encloses or suppose like just covers all of VP, then you would expect that permanent should be, or some other polynomial VNP should be outside this. Right. So this is the technique. So now let's try to, instantiate this in a certain setting. So first let's do some warm-up exercise, right? Okay, so we'll work with complex numbers, unless mentioned otherwise. I don't want to get into any problems with roots of polynomials and so on. So suppose the universe that we are considering for now is just univariate polynomials of degree at most 3, right? So any such polynomial can be expressed as a vector of length 4, right? So the universe is just C to the 4. Any member here is also a univariate of length 4. Notice. Okay. And suppose the class of simples that we have for now is just polynomials that are cubes of single linear form. Okay, so this, or other, in other words, these are univariates that have a triple root at a certain point. Right, all the roots are just a single point. Okay, and let's not worry about the explicitness for now. Let's just focus on this. Okay, so what is and now suppose we don't know a polynomial that does not satisfy this property. We don't know a polynomial that is outside the C. So one way to do this, one way to find such a polynomial will be to just see, okay, just expand alpha y plus beta the whole cube. So what you will get is that you'll start seeing the structure in the coefficients of such a polynomial. So you have alpha cubed, 3 alpha squared beta, 3 alpha beta squared, and beta cubed. And once you stare at this enough, you will say that, oh, I mean, you suddenly see structure. What you see is that if you have a polynomial that is in C, let's call the coefficient vector ABCD, then you notice that 9AD minus BC, I hope that is correct. Yeah, 9AD minus BC is always 0 for this polynomial, right? And yeah, and now if you draw this set of all ABCDs for which this equation is 0, you get this set script P, say. Okay, and because everything in C has this property, you have that C is a subset of P. Script C is a subset of script P, or rather calligraphic C is a subset of calligraphic P. Okay, so one thing to note is that it's not necessary that everything that is in P is also in C. I don't want to capture the set C, I just want to cover it. Okay, this is a very, I mean, it will become clear why this is a very crucial property. So as long as I have this, so now what I can do is, and so notice that this is a very easy equation. So it's easy to not satisfy it. Okay, so for instance, I can just choose B and C to be 0 and A and D to be 1, and I suddenly have a polynomial that is outside C. Okay, so this is what we want to do, and this is what this is a particular natural. So this is a particular lower bound or a hardness result that we proved using this natural technique. Okay. Okay. So I forgot to mention. So at any point of time, if there is any question, just unmute yourself and interrupt me, because yeah. Okay. So now what I'll try to do is let's try to extend this to the multivariate world. Okay, and this will get us to the algebraic natural proof setting, which was defined recently. Okay, so now what is the universe? So now we are looking at n-variate polynomials of degree, let's say at most d, and this d is poly n as mentioned earlier. So how many monomials does such a polynomial have? It has n plus d choose d monomials, and let's call this capital N. So just like earlier, all our polynomials, we looked at them as coefficient vectors of length 4. Now we'll look at them as coefficient vectors of length capital N. Okay, so the universe is c to the n, c to the capital N. And now what we want to do is we want to say C is VPN, the class of simples. D is VNP, the class of explicit objects. And now what we would want is a property P, or sort of a set of weak or a weakness P, right? And what is the property that we want from this weakness? That if you feed any polynomial, if you feed the coefficient vector of any polynomial from VP, the class C, then it should vanish. It should just output 0. Right? And in particular, if you draw the 0 set of P in this diagram, then it should cover VP. Okay. And hopefully, if this is simple and everything is nice, then you will have something explicit which is not a root of P, something here, right? In this crescent sort of a shape, there will be something here. And so what do you mean by simple, right? We have already defined simple. We know what it means for a multivariate polynomial to be simple. We just want P to be in VP, right? So this is the algebraic natural proofs question. We'll come back to this again. We'll state it formally. But this is what it is. You want a property P that is simple to compute, which also covers all of VP. Right? So let's just look at this again. Okay, so just as before, you have n and d. D is polynomial related to n, and capital N is n plus d choose d. And you're looking at some class of n-variate degree d polynomials. Now, more general than VP, need not be VP. So you can talk about natural proofs for this class C. Okay, so a non-zero polynomial P on capital N variables is a VP natural proof for C if firstly it vanishes on everything in C, and secondly it itself is in VP, right? So it's called a VP natural proof because it is itself in VP. This VP and this VP is just it's the same VP appearing in two things, right? Yeah, so this is the definition. And okay, so what do we want now? What will be the best case scenario? We would want a P that is a natural proof for VP. Okay, so it vanishes on VP and it does not vanish on VNP. This will be like the dream. If you can find such a thing, you'll be very famous very quickly, right? So this is what we want to do. And a barrier is basically when this does not happen, right? So a barrier would be when there is no such P that is efficiently computable, which witnesses the separation of VP and VNP. What does this mean? Either it does not vanish on VP, all of VP, or if it vanishes on VP, it also vanishes on VNP. Okay, so basically the negation of this. There is no P that does this, right? And this is essentially going to say that natural techniques, which we saw what natural techniques mean, natural techniques cannot separate VP and VNP.
So,
right?
Anamay?
Yeah.
So why was it important that P be efficiently computable?
A good question. Yeah, so that's a good question. So it's sort of a choice, but one thing that would help us is that if P is efficiently computable, then we can expect that a non-root of P lies in VNP. A non-root of P is sort of explicit in some sense. Yeah, but it's not a very well-founded reason. It's just intuition, I think, unless I'm missing something.
Thank you.
Yeah. Okay. Yeah. Any other question on this? Because this should be sort of clear. I think I have 10 more minutes. Yeah. Yeah. Okay. So I think this is clear. So then then the question, is there an algebraic natural proofs barrier, right? Is there any P that is there no P that separates VP and VNP? Right. So where does this come from? So this is heavily motivated from the natural proofs work of Rasburov and Rudich from 97, 95 from the Boolean world. And they showed that if one-way functions, something called one-way function, some pseudo-random object, if they exist, then there are no natural proofs for the poly-sized Boolean circuits, right? P by poly. Okay, and these one-way functions, I mean, the existence of one-way functions is widely believed, and it's also heavily used in, I mean, modern cryptography. So this basically means that there are no natural proofs for P by poly. So there is a natural proofs barrier in the Boolean setting. Okay, so what do we know in the algebraic setting? So in the algebraic setting, this algebraic natural proofs concept was introduced by two independent works, one of Forbes, Spielka, and Volk, and the other by Grochov, Kumar, Sachs, and Saraf. And what they showed is that a similar statement. So you don't need to understand what succinct heating sets are, but what it basically means that if the class VP has polylog and succinct heating sets, so this again some pseudo-random object, but of, I mean, it's really succinct. It's like polylog n. So you have something of size poly n, and you're sort of fooling it by something of size polylog n in some loose sense, not very. But again, a similar flavor. If a certain de-randomization assumption holds, then there are no natural proofs for VP, right? Which means there is a barrier. Okay, good. But there is a small caveat here. I mean, this succinct heating sets object, so these are not well-studied objects. So it's difficult to just look at this and make up your mind on whether there is or there is no natural proof barrier. So this is kind of open. I mean, open as in we don't yet know. I don't think many people have made their mind on whether there is a barrier or not. Okay, so something towards that was done in the same work of Forbes, Spielka, and Wolf. What they showed is that what they did is they constructed explicit succinct heating sets. They constructed really simple, like depth 3 succinct heating sets of course, again, polylog n variables. Okay, against some weak classes like depth 3 powering and so on. So these classes are really weak. We know strong lower bounds against these classes. But again, so because of that, what happens is you gave a much better de-randomization object. I mean, much better pseudo-random object that works against much weaker classes. So this is some weak evidence, but it's not, I mean, it's incomparable. So this does not mean anything directly. It does not imply anything. So this was the setting before the two works that we came up with last year, which I'm not now going to just go over. Okay, good. So what are our results? So now just recall what is the dream. The dream is to find a capital N variate polynomial P, which is itself in VP. I mean, which itself has poly capital N size circuits and degree. Okay, such that firstly it vanishes on all of VP, and secondly it does not vanish on something in VNP. Right? It separates VP and VNP, or witnesses the separation of VP and VNP. So here is what we proved. So this is the first result that we found out. So the first thing is, so firstly, so consider VP prime, which is the class of all polynomials in VP that additionally have small coefficients. Let's say -101 for now. Okay, and notice that this is just, I mean, I want to stress on the fact that this is a statement only about polynomials. The circuits, I mean, the reason why this polynomial is in VP, that circuit could use arbitrary complex numbers. I don't care. If the final coefficients are just -101, then it's in VP prime. So in particular, determinant is in VP prime, irrespective of it using arbitrary constants. Okay, so VP prime is such a class. Okay, so we showed that there exists a polynomial that itself has small circuits. So I should write in VPN here. So there exists a polynomial P in VP of capital N that vanishes on all of VP prime. Right, so this sort of shows that for all the interesting polynomials in VP, right? Because all the polynomials, I mean, almost all of the polynomials that we know of, which are well studied in algebraic complexity, they have small coefficients. So if you look at all interesting polynomials inside VP, then they're all in VP prime. So we showed that there is a proof for this interesting subclass of VP.
Anamay, only 1
Yeah.
minute is left.
Sorry?
1 minute is left.
Yeah, but I started like 5 minutes later. So
Oh,
give me
okay.
2 minutes maybe.
Sure,
Yeah.
sure.
Okay. Yeah. Yeah, so this was the first result. And the second result was as follows. Second result shows that, so assume that the permanent is 2 to the n to the epsilon hard. It's exponentially hard for some constant epsilon. Okay, so maybe 2 to the n to the 0.1 hard or something. Okay, then what we showed is that if you have a polynomial, capital invariant polynomial that vanishes on all of V and P, then it must have super polynomial size. It requires super polynomial size to compute it. So if you believe in this assumption, if you believe that the permanent is exponentially hard, then this essentially means that there are no natural proofs for VP, for VNP, sorry. Right? So this is, I mean, it's a very nice approximation for the dream, I feel, but of course, there is some caveat, which I will now come to. And I'll just go over this quickly. I'll take a question at the end, maybe. So yeah, so let me just go over the first result more clearly. So just as earlier, right, this n little d and capital N is the length of the quotient vector. There is a P, there is a capital invariant polynomial P, proof P, which vanishes on all of VP prime, everything in VP with coefficients in plus minus 1. Itself is in VP, so it's a VP natural proof against VP prime. And yeah, I mean, just to mention that it is non-trivial. I mean, it's easy to just vanish over everything that has such coefficients, but it is not that, of course. So it does not vanish on many polynomials that have plus 1, minus 1, 0 coefficients, right? And as I had mentioned earlier, almost all well-studied polynomials. So for instance, all polynomials that were spoken about in the last few hours they have small coefficients. Okay, and okay, and yeah, so one thing to note is even permanent is because permanent also has small coefficients. So such an equation could possibly prove permanent is not in BP, right? It's not unthinkable, right? Yeah, so a small caveat is that we also are able to prove, using the same techniques, we also prove that a similar result holds for VNP as well, right? So same VNP prime again, and a similar result holds, right? And the idea in one line of this is that if you have hitting sets for a class C, then you get natural proofs for the class C prime. Okay, that's all that I would say about this now. And yeah, I want to say something about the second result as well. So the second result, as I had mentioned earlier, if you believe that the permanent is exponentially hard, then all that we are saying is there are no natural proofs for VNP. Okay. Yeah. And what this means is that the restriction on coefficients is crucial for the existence of easy proofs, at least for the case of VNP. Because as I mentioned on the previous slide, there are easy proofs for VNP prime, right? There are easy proofs for VNP prime. So once you allow large coefficients, suddenly the complexity of a proof just becomes super polynomial. So that is one message that you can take from this. Okay, and here again, the idea, if you are aware of the Carbonet-Sim Pugliese generator, then just the idea is just that you can make the Carbonet-Sim Pugliese generator VNP succinct for whatever that means, right? And for this, you use the notion of Reed-Solomon codes that Siddharth had spoken about earlier. Okay, so yeah, I just want to take one more minute and spend some time on this. What all this means. Okay, this is, I would say, this is the most important slide of this. Okay, so what does this mean in the context of VP natural proofs for VP? So suppose you believe in the existence of VP natural proofs for VP, right? Suppose you believe there is no barrier, then what these results put together, or just the second result, means is that there is a natural separation between VP and VNP, as long as you also believe that permanent is exponentially hard, right? Which is not much to ask, right? So if you're a believer, then you should be happy. There's a natural separation between VP and VNP. Okay. In fact, any natural proofs that you will find for VP will separate VP and VNP because VNP has no natural proofs. And if you are one of these people, which is me as well, then what you should do is you should try to prove existence of natural proofs for VP, maybe using some standard hardness assumptions. Okay. Now, on the other side, if you are a skeptic, if you don't believe that VP natural proofs exist for VP, then you must now believe that the pseudo-randomness of VP is coming from large coefficients because of the first results. I mean, what happened with VNP should also happen with VP, right? What happened with VNP in our second result should also happen to VP. And for now, at least, it seems like our proof in the second result, it seems to require the power of VNP, like closure under exponential sums and so on, and exponentially hard polynomials, right? But then if you are in this group, then you should again try to prove non-existence of natural proofs for VP, maybe again using standard assumptions possibly. And even if you don't care, I mean, even if you were not decided, then maybe both these results, looking at both these results and looking at the whole story, maybe it should motivate you to look at this topic in more detail, right? This is just interesting, at least, if not anything else. So that's all that I wanted to say. Yeah, thank you.
Thank you, Anamay. If anybody has any question, please go ahead. We have time, actually. We have a break for half an hour.
Oh, sorry.
Hi, Anamay.
Hi.
So basically, like I had two questions, like constructibility and largeness. Usefulness anyway is taken care of.
Mm-hmm.
it's useful against all of VP.
Yeah.
Like Jaykumar already has a constructability question.
Yeah.
And then the largeness, how is largeness useful over here?
So I think so. Okay, so there are two things to it. So the first thing is, so largeness comes for free if you are in some general setting. So for instance, the first result that we have, right, the first result that gives proofs for interesting subclass of VP, that is not large in the usual sense of large. It's not 1 over 2 to the poly dense. It's 1 over 2 to the quasi poly dense, I think. Yeah, so that's not large, but I mean, the way I understand it is that I think so, but okay, but I mean, so that happens to us because we are working with this restricted coefficient setting. So not all inputs are valid inputs for us, which is why that largeness drops. Otherwise, whenever you have a low degree polynomial, it just comes for free, which is why we don't explicitly mention largeness in the definition of a natural proof. But I would guess that it's just, I mean, it just so happens that you want to say that, I mean, because you are saying that the proof captures a certain weakness, you want to say that most objects are not weak. So in that sense, I guess it just comes down to where you draw the line for most. Yeah, I think I don't have a better answer than that. Why largeness is necessary?
Basically, even when you say there exists a polynomial that does not vanish, that is essentially saying it's outside your largeness, right? Am I making sense? No.
Yeah. No, it's not outside large. So okay, so here something weird happens. So in the algebraic world, the largeness is on the non-root of P. Non-roots of P are, I mean, most of the things are non-root of P. So
okay.
that's how the largeness. Yeah.
Okay. Sorry.
No, that's so I think in the Boolean world, whatever has a property is outside. I mean, yeah.
Yeah, I'm done. So.
Okay. Yeah. Thank you.
Any further questions? If no, then let's thank Anamay again. And we'll meet at 4 after half an hour. Thank you.
Yeah. Thank you.